Okay, time for a very interesting discussion on time period of a simple pendulum. This is something which you have used in the lower classes, right? And we're going to try to understand how this equation has come in. The equation that I'm referring to is time period of a simple pendulum t is equal to 2 pi square root of L by G. This is the equation that gives the time period of a simple pendulum. In the lower classes, you would have used this to solve numerical questions and also to probably do a practical in the laboratory on finding out the time period of a simple pendulum. At that point in time, we did not look at how this equation came into being. We just simply used it and then we tried to find out the time period. The objective of this video is one, to show that the motion of a simple pendulum is SHM, a simple harmonic motion. That's one. And the second objective is to confirm or derive this equation to t is equal to 2 by L by G, where of course L is the effective length of the simple pendulum and G is the acceleration due to gravity. Right. So let us say we have a simple pendulum. This is the rigid support, and let us say this is the equilibrium position of the simple pendulum. So it is in its equilibrium position, and let us say we apply a disturbing force onto this, so it will start moving in this direction, and let us say it turns through an angle theta and comes in this particular position. It turns through an angle theta. Let us say the effective length of the pendulum, of course, is L, and the mass of the simple pendulum is equal to M. Now, when the pendulum comes in this position, there are two things which are observed. The first thing that is observed is that this particular pendulum has a tendency to go in this direction. We know that this is trying to go in this direction. It is trying to go back to the equilibrium position. How do we know that? We know that because the pendulum's velocity keeps on decreasing and finally it becomes zero and then it starts going in this direction. The velocity is constantly decreasing. That shows us that this pendulum has a tendency to go back to equilibrium position. So one thing that we are able to see is that there is a restoring force which is observed. The second thing observed is that this string is tight. So there's a tightness in the string. The string is not slacking, it is remaining tight. So there's some tension in the string. So these are the two forces which we are able to observe. One is the restoring force trying to get this pendulum back, and secondly the tightness in the string. How do these two forces come into play? I'm sure you have guessed. They come into play because of the weight acting in the downward direction of this pendulum. So this is mg. As we said, mass of the pendulum is m. Essentially the mass of the pendulum is the mass of the bob. So this force mg is acting in the downward direction, vertically downwards. And this mg generates these two forces. Because this mg can be broken up into two components. Right? There can be a component taken like this, and there's another component in this, like this. If this is theta, this will come out to be theta. And if this is mg, then I can prove that this particular component of mg is mg cos theta, because this is the adjacent side to theta. This is the opposite side to theta. So this component will be mg sin theta. And as you can see over here, mg cos theta is acting in the downward direction. Therefore, it is kind of pulling this string in the downward direction. And therefore, the tightness in the string is observed. So this tension will be equal to mg cos theta in equilibrium position. And secondly, mg sin theta is acting in this direction. That means it is trying to take this back to the equilibrium position. So this is how these two forces come into existence. And this force, mg sin theta, is the restoring force. Fr is equal to mg sin theta. The magnitude is mg sin theta. I'll attach a minus sign because it's a restoring force. It is trying to decrease the velocity. So Fr can be taken as m alpha is equal to minus mg sin theta. Force is mass into acceleration, where alpha is the acceleration of the bob of the pendulum. So alpha can be written as minus g sin theta. Now, this angle is theta. Let us say we focus our attention on this right angled triangle, this right angled triangle. Let me give it names. Let me call this O, let me call this A and let's call this B. Therefore, alpha will be equal to sine theta. Sine theta is opposite side upon the hypotenuse. Right? So this is the right angle triangle. So this is the hypotenuse, which is L. What is the opposite side? Opposite side is AB. Now AB is the displacement from the mean position. So this can be taken as displacement. And displacement, I will use the symbol X, say for example. X represents displacement from the mean position upon hypotenuse, which will be equal to L. Therefore, alpha is equal to minus G upon L X. Now, in this equation, G and L are constants because acceleration due to gravity would remain constant at a given location. The length of this pendulum is constant. So this is constant, and therefore I can write down alpha is proportional to minus x. And what do I conclude? When the acceleration is the acceleration is proportional to displacement and is opposite to it, that means this particular motion is simple harmonic motion. This was the essential condition for simple harmonic motion. So thus I have proved that the motion of simple pendulum is simple harmonic motion because acceleration is proportional to minus x minus displacement. Okay, let me now go to the second part. Let us rearrange this equation. Let me rewrite over here. Alpha is equal to minus G upon L into x. Therefore, x upon alpha will be minus L by G. Now, when we discussed simple harmonic motion, we had proven that the time period of simple harmonic motion is 2 pi square root of displacement upon acceleration. If you don't recall this, refer to a previous video on simple harmonic motion. There we have got this equation. So T will be equal to 2 pi displacement upon acceleration. This will be x upon alpha. And x upon alpha is L upon G. Let me rewrite x upon alpha is equal to 2 pi into x upon alpha is L by G. Now I'll ignore the minus sign because the minus sign only indicates that the direction of acceleration and displacement are opposite. And time is a scalar quantity, so I will not worry about the minus sign. That is not going to change the value of periodic time. So I'll simply write x upon alpha is L by G. And thereby I come to this equation T is equal to 2 pi square root of L by G. Right, so we have achieved both these objectives. Final thing that we need to remember about this is that the value of theta has to be small, say for example between 5 degrees to 10 degrees for us to be able to use this equation. If the value of theta increases, that means the amplitude goes very high. This does not hold good. So this is applicable only for smaller values of theta, maybe between 5 degrees to 10 degrees. Thank you.